Swayam Prabha. Digital India. Educated India.
Hello everyone. As you know, we are having a discussion on resistance as derived from the formalism that we discussed and as we understand from our classical understanding of semiconductor devices. So, we are contrasting these two type of or the resistance from these two formalisms. And the classical understanding of resistance says that in a typically in a 1D, 2D or 3D in any kind of conductor, the resistance is directly proportional to the length of the conductor, like this. In case of 1D conductor, it is just the length of the it is proportional to the length of the conductor. In case of 2D conductor, it is directly proportional to the length, inversely proportional to the width. Similarly, in 3D conductor, it is directly proportional to the length, inversely proportional to the area. This constant of proportionality is known as the resistivity, and the inverse of resistivity in the material is known as conductivity. That is the classical picture of transport that we have in our mind. From our formalism of the general model of transport, we deduced this expression of the conductance of the device. It is G is equal to 2q square by h integration of TE ME over the Fermi window minus del F by del E times dE. And we started the discussion for low temperature case, what happens at low temperatures in a ballistic conductor. And at low temperatures in a ballistic conductor, the conductance turns out to be 2q square by h times MEF. This is at T equal to 0 Kelvin for ballistic case. Okay. This term 2q square by h is known as the quantum of conductance. It is the conductance of the single channel of the electron in the devices, and its value is 1 by 12.9 kilo ohms. From this sort of derivation or this analysis, we could see that for a 2D conductor, 2D ballistic conductor, the resistance is independent of the length, as opposite to the our classical understanding, our conventional understanding of the resistance. So, that is the key difference. So, that is why in our modern nanoscale devices, we can no longer use the conventional understanding of electron transport. We need to have a fundamentally different kind of theory of transport, and that is what we are doing in this course. After that, we are currently studying the transport in studying the resistance in ballistic conductor at 0 Kelvin, but now a wide conductor. That is where our discussion was stopped in the last class. So, we have a conductor let us say of length L, width W, and it is a ballistic conductor, which means that electrons do not collide with anything in between, they directly go from the left terminal to the right terminal. And because of the temperature being 0 Kelvin, now we can say that all the electronic states up to energy EF are filled. All electronic states are filled. So, if we need to calculate the resistance here, we again begin with the same expression of the conductance, which is 2q square by h. In ballistic case, Te is 1, so we are just left with Me and essentially minus del F by del E dE, and at 0 Kelvin this expression essentially boils down to MEF. This is the ballistic conductor at 0 Kelvin. Now, this term, this MEF, this we can put it the form of this from our derivation, which is essentially W times square root of E minus EC divided by pi h bar to m star as well. Or we can correlate this term to an experimental parameter, which is generally the sheet carrier density in a 2D conductor, which is the number of electrons per unit area. So, this is given, this can be deduced from the experiments. For example, I gave you an example of Hall effect experiment. So, if we know the Hall coefficient of the material, we can deduce the sheet carrier density by measuring the Hall voltage of the that particular material. So, this parameter is generally available from the experiments, and we would like to correlate this MEF with this parameter, and for that we need to go back to the K space. So, this is Kx, Ky. The conductor physically looks like this. In x direction it has certain length, in y direction it has certain width. So, the allowed K points or the values of the K points where a valid electronic wave function exists in this material is given by the solution of the Schrodinger equation, and we obtain these kind of points. These are essentially pi by L, 2 pi by L, 0. On the y axis we have pi by W, 2 pi by W, and so on. And since the temperature is 0 Kelvin, all the energy states up to EF are filled, which means that all the K points up to K equal to Kf are filled. K from 0 to Kf are filled, where Kf is given by square root of 2 me 2 m star EF by h bar. This comes from the EK relationship. Okay. So, the total number of electrons will be inside this circle of radius Kf. If this is the radius of this circle is Kf, the total number of electrons or the sheet carrier density in the material will be given by the area of this circle in the K space. And what is the area here? Or number of electrons at T equal to 0 Kelvin will be number of electrons, electronic states, more precisely electronic states in the circle of area covered by radius Kf. Okay. Now, how many electrons are there in this circle? That will be given by the number of electrons will be the area of the circle divided by the area occupied by one electron or one electronic state. So, if we divide the area of the circle by the area of one electronic state, that will give us the total number of electronic states in the, or total number of electrons in the system. So, essentially this is what we need to calculate in this case, and the area of the circle is simply pi kf square, but what is the area that a single electronic state occupies? So, in the K space, if we have a close look on the K space, these are the okay. So, generally this is the area occupied by one electronic state. However, we also saw in our discussion of density of states that this set of k values and this set of k values and this set of k values and this set of k values, they essentially represent the same wave function. So, what we can say is that the area occupied by an electron is this, or if we consider the spin, this is the area occupied by two electrons. So, two electrons, one with upspin, one with downspin, will occupy this amount of area. So, area of one electron will be, and what is the area? This is 2 pi by L length and 2 pi by W width. So, the area will be 2 pi by L times 2 pi by W. So, it will be 4 pi square by L times W, or 4 pi square by A. This is the area occupied by two electronic states if we consider the spins as well. So, the area occupied by one electronic state is 4 pi square by A by 2. So, it will be 2 pi square by A. Okay. Now, we can sort of see the total number of electrons in the system from this expression. So, total number of electrons will be the area of the circle, which is pi kf square divided by the area of the single electron, which is 2 pi square by A. So, pi, so it is A times kf square divided by 2 pi, and the sheet carrier density will be the total number of electrons divided by area. So, it will be n by A, which means ns can be written as kf square by 2 pi. Okay. So, that way we have a relationship between ns and kf vector. Okay. In other words, this kf is essentially square root of 2 pi ns. So, let us just keep this equation with us. Ks is square root of 2 pi ns, and if we use this expression for a 2D conductor, which is essentially the number of modes in a 2D conductor is W times M2DE, also written as W times K divided by pi, or W divided by lambda b by 2, where lambda b is the de Broglie wavelength of the electrons. Okay. So, using this expression now, this M2D EF, from here we can see that M2D E is actually W and W will go away, K by pi. So, M2D EF is Kf divided by pi, and from the previous analysis, Kf is square root of 2 pi ns, this divided by pi. So, M2D EF now is square root of 2 ns by pi. So, we now have this number of modes parameter in terms of the basic or experimental parameter of the device, ns, in terms of ns. And if we replace this in the conductance expression, the ballistic conductance at 0 Kelvin of the conductor is 2q square by h times m EF, where m is W times M2D EF. So, it becomes W times 2q square by h square root of 2 ns by pi. So, this is the finally the ballistic conductance of a 2D conductor, 2 ns by pi. Or the resistance, ballistic resistance will be the inverse of this, which is essentially 1 by W h by 2q square square root of pi by 2 ns. Now, as is also clear from this expression that the ballistic resistance is independent of the length, as we also expect, because the electron is not colliding throughout the length. So, that is why the length is not important in resistance. It is, however, inversely proportional to the width, because more the width, more will be the number of modes in the transistor, more will be the conductance, less will be the resistance. Apart from that, it is inversely proportional to the sheet carrier density, which is also expected, because more the number of electrons available in the conductor for transport, less will be the resistance, or more will be the conductance. And apart from that, we have a fundamental constant, or the quantum of conductance constant in these expressions. Okay. So, this is pretty much what we have in our 2D conductor at 0 Kelvin and with a finite width. Okay. Up to now, we have only considered the case of 0 Kelvin at extremely low temperatures, but now let us consider a more realistic case. So, the case when the temperature is room temperature, or it is beyond, or it is above 0 Kelvin temperature. And because of this, because of the room temperature case or higher temperature scenario, we can no longer make this assumption. We cannot approximate the Fermi window by a delta function, because this is only possible at 0 Kelvin. So, now this needs to be explicitly calculated, and this becomes one of the main things to do in these calculations actually. So, so here we have again we in order to calculate the resistance of a 2D resistor at room temperature, let us say, we start with the formula of the conductance, which is 2q square by h integration of T e m e minus del f by del e d e. And now this term needs to be explicitly calculated, and this is a tedious calculation, I would say. Okay. So if we put the Fermi function explicitly in this expression, it becomes G is 2q square by h Te me minus del by del E 1 by 1 plus exponential E minus EF by kT integrated over energies. This derivative minus del by del E, so this minus del by del E F is equivalently can be written as del by del EF of F. So minus del F by del E can be written as del F by del EF. And by making this substitution, we can essentially bring this derivative term outside the integral. In ballistic case, Te is 1. So if we make this substitution, the ballistic conductor at the conductance of the ballistic conductor at higher temperatures is it becomes, if we bring del by del EF integration of ME 1 by 1 plus exponential E minus EF by kT dE. Now this entire calculation, this entire integral needs to be evaluated along with this differential, and this becomes a non-trivial calculation actually. For most of the practical applications, this becomes a difficult thing to do. So that's why this is finally the, if we also write it down explicitly, ME, which is essentially, so if we write down ME to be W times square root of 2m star E minus EC divided by pi h bar. So then this ballistic conductance formula essentially becomes, this formula can be written down as G ballistic is equal to 2q square by h del by del EF. Now if we put, instead of ME we put this, then W by so this may come out, W by pi h bar will come out, W by pi h bar will come out, and even square root of 2m star can also be taken out. We are left with this derivative term and the integral of E minus EC power half divided by 1 plus exponential E minus EF by kT dE. So this is finally, this formula will be or the conductance of the ballistic conductor will become. It has a range of constants here, then a derivative, and then an integral. So this is a combination of, so we need to first integrate, then take a derivative with respect to EF. And as I mentioned that it is a difficult thing to do. So and that's why generally this expression, which is essentially the same that was there in the, this is evaluated, this kind of integrals are separately evaluated and they are separately categorized as Fermi-Dirac integrals. Fermi-Dirac integrals. Because these kind of integrals, they appear quite often in solid state physics, especially in the ballistic transport and in the calculations of the conductance, or even in the calculations of the IV characteristics at room temperature. Similar kind of integrations appear there. Okay. So these are known as the Fermi-Dirac integrals, and the way to evaluate them is to make this change of variables. So a new variable eta is defined, which is given as E minus EC by KT. Generally in these derivations it is written as Kb times TL. Kb is the Boltzmann constant, TL is the lattice temperature, which we are in short writing as K times T. And another parameter eta f is defined as EF minus EC by KT. So if we make this change of variables in this equation, then this integral, essentially this part of the integral del by del EF, this derivative and integral square root of E minus EC divided by 1 plus exponential E minus EF by KT dE. So this changes to square root of KT del by del eta f integral this, if this limit is 0 to infinity, this is also 0 to infinity, square root of eta divided by 1 plus exponential eta minus eta f d eta. This is just consider this to be a small exercise. Just put these variables E minus EC, replace E minus EC by eta KT and EF minus EC by eta F KT, and then see how this derivative and integral changes. This is the answer actually, this is how it changes. So just do it yourself, that will give you a more hands-on feel of this expression. So ultimately in the calculation of the conductance of the material, this derivative along with the integral, it changes to this. So finally we can write down the ballistic conductivity of a 2D conductor, 2q square by h w times square root of 2m star kt divided by pi h bar del by del eta f integral from 0 to infinity square root of eta 1 plus eta minus eta f d eta. So these kind of integrals are known as the Fermi-Dirac integrals, and depending on the power of eta in the numerator here inside the integral, the order of the Fermi-Dirac integral is defined. So in this case the power of eta is half, so this is the Fermi-Dirac integral of order half. Okay. So and this is how precisely the Fermi-Dirac integral of order half is defined. It is 2 by square root pi integral 0 to infinity eta to the power 1 by 2 divided by 1 plus exponential eta minus eta f dn. So it does not involve the derivative here. Yeah. So earlier I mentioned that this entirely is defined as the Fermi-Dirac integral, but it is only this part that is defined as the Fermi-Dirac integral. And there is an interesting property of the Fermi-Dirac integral, that if we take a derivative of the Fermi-Dirac integral with respect to EF or eta f, so if we do this with Fermi-Dirac integral, let us say of order n, then generally the Fermi-Dirac integral of order, it becomes a Fermi-Dirac integral of order n minus 1. So, in this case, in the case of calculation of conductance for a 2D conductor, 2D ballistic conductor at room temperatures, we have a Fermi-Dirac integral of order half, and we are taking a derivative with respect to eta f. So, finally, it will be a Fermi-Dirac integral of order minus half, because, and this maths, we are not going in this in the detail of the maths, the maths of Fermi-Dirac integral, but this is how finally everything will look like, and this should be order minus half actually. So, finally, the conductance of a ballistic 2D ballistic conductor at room temperature will be given by a set of constants and a Fermi-Dirac integral of order minus half. Okay. So, I will let you think about this replacement of variables by this change of variables through which we obtained this Fermi-Dirac integral formulation, and I would recommend you to go back and look at the Fermi-Dirac integrals independently. I will also share some materials on them, and we will start the next class this point onwards. We will have slightly more deeper understanding of this final expression, and that will essentially conclude the discussion of the conductance of the ballistic conductor at normal temperatures. Thank you for your attention. See you in the next class.